Hello, everyone, and welcome to Tech Talk session number 21. So we are certainly making a lot of progress here. So today we are going to be speaking about sweep frequency response analysis. It's an SFRA acceptance test that is conducted by Northeast Power Systems, Inc. You will find that this test is very interesting and it reveals manufacturing errors that we might have in our manufacturing process. But it also serves as a tool for our customers should they have some type of problem in the field. So we're going to be talking about how the test is conducted. And then we will actually do a factory test today. We will go back out into the factory floor and show you how this test is conducted. So it's going to be a very interesting tech talk today. So let's get on with the presentation. So again, don't forget, if you have questions, hit the question box. You may ask the questions in Spanish if you like. We have Rodrigo Dunner. And at the end of this presentation, please send us an email. We will get you the PDH credit for this Tech Talk session. So perhaps we can bring Rodrigo on for a second. You can meet Rodrigo. Hi, Rodrigo. How you doing?
Well, hello, Paul. Muy buenas tardes. A todos. Primero que todo y muy brevemente, a modo de introducción, remarcar nuevamente que NEPSI diseña y fabrica bancos y filtros metal enclosed para distintas aplicaciones. Mi nombre es Rodrigo Dunner, soy el encargado de ventas para Latinoamérica y otros países también de habla hispana. No duden, por favor, en consultarme a mi correo electrónico rodrigo.dunner@nepsi.com si tienen consultas, dudas con respecto a especificaciones técnicas o necesitan propuestas presupuestarias. Estamos acá para ayudarlos. Y hoy día tenemos una muy buena Tech Talk relacionada con las pruebas de barrido de frecuencia para nuestros equipos. Así que los dejo con Paul para proceder, digamos, a la presentación. Muchas gracias.
Okay, yes, thank you, Rodrigo. I think in English he's saying, please ask questions and don't forget to contact him with questions that you may have or feasibility, quotes, budgetary prices, things like that. So reach out to Rodrigo if you're in Latin America and he can certainly help you with his projects. Don't forget what NEPSI does. NEPSI is a manufacturer of metal enclosed capacitor banks and harmonic filter banks. We specialize in these medium voltage systems. So if you have a project, bring it to us. We can help develop that project with you. So today we are talking about sweep frequency response analysis. It's a test method that NEPSI has started approximately 2 years ago. It's a factory acceptance test that we do on all of our harmonic filters. And essentially what it does is it helps to guarantee that the tuning point and the damping factor and other various aspects of that harmonic filter meet the specification. So if you, up on the screen here, I show a very complex harmonic filter system. This particular harmonic filter was used for a black start project, but it's a very complex harmonic filter system. You can kind of see here that we have a standard notch branch, a high pass branch, and then what I would think is classified as an H filter. But the system continues on through. It actually continues on through to another bus bar where we have more complex filters. So a very, very complex harmonic filter system. So how would you know? How would you know if this thing is all connected up? There are many manufacturing errors that can occur in the process of doing this. We can maybe misconnect the reactors, or maybe the resistors are wrong. These are things that would be a concern. Perhaps the capacitor is nameplated incorrectly. So, we send this stuff out into our factory floor, and then they build the equipment. What is the best way to test it? Well, we believe that SFRA testing is by far the best way to test a harmonic filter system. Connect it at the terminals and check, well, what does the impedance profile look like? And we're going to kind of show this today. But what does that impedance profile look? The SFRA test set is a test set that's commonly used in testing transformers, transformer windings, and major power transformers. So it's used in the power substation to check the health of a power transformer. If there is any kind of shift in the winding of a power transformer, its capacitance and impedance characteristics change, and you'll get changes in the shape of the curve. So in a substation environment, you're typically using it on the power transformer to determine the health of the transformer. Has any change occurred from the date it was manufactured to some time in the future? Say you had a fault on that transformer and the winding shifted a little bit. Well, its capacitive characteristics would change and you would get a shift in that impedance profile. Well, so NEPSI investigated about 2 years ago, well, perhaps we can use this instrument to test our harmonic filters. Because really what this instrument is doing is it's injecting a current into the filter here, and it's reading a voltage across this terminal. So essentially it's taking V divided by I, and it's calculating the impedance of the harmonic filter. And it's doing that through a range of frequencies. And this device is very sophisticated. It's doing sometimes 10 samples per frequency point. And what we are able to do is determine, well, what is the impedance throughout the whole range of that harmonic filter, but not only impedance, but also X and R, the phase angle, and more. So we really do be able to get a very good characteristic of the filter. Typically, we're connecting phase to phase here, and we're measuring basically the impedance profile through one phase, if you can think about this, through the neutral, back to the other phase. So we're capturing an out and back path, which means that the impedance value we're connecting to or we're reading is double what we would actually see line to neutral. It's a line to line impedance value. When you look at the when you look at a typical, and this is for this complex harmonic filter system, when you look at it, there was a harmonic study that was conducted, and that harmonic study came up with a filter design, and that filter design was put into the power system model, and then the expected performance was discovered or looked at and determined. So the question for the most part is, after we build a filter, how far did the impedance profile of the harmonic filter deviate from the study? All right. If the impedance profile is different, then the results that the study revealed or provided would be different. And so what we do is we ask, if we're not involved with the harmonic study, we ask, well, give us the impedance profile that you studied. What is it? We want to see it. And we will overlay that with what we measure in the field. And this is actually for the harmonic filter that I showed on the previous slides. It shows that we can get a very good representation of the filter impedance, and we can reveal that we actually are getting very close results. So we have the 3 phase-to-phase impedance values being compared against the theoretical. And in this case, you can kind of see what the result was. So I'm going to flip over and just kind of show you how this is typically done. If we do the harmonic study, we use a program called Easy Power. And I just took a very simple system here in the actual harmonic filter. In this case, we have, let me go over the database. Okay, let me go to database. You can kind of see here we have 3 harmonic filter branches, and they're all high-pass filter branches. And I can put this thing into harmonics mode. I can double-click the bus bar, and I can actually get the impedance profile. And on the x-axis here, we have ohms, and x-axis, let's get that right. X-axis we have harmonic number, and the y-axis we have ohms, and we can get that impedance profile. And we can compare that to what we would get from this program. So we take the data here, we highlight it, we bring it into Excel, and then we plot that data. And we then develop a report. And that report looks like this. Okay, so we have an explanation, the project number, and then we get our impedance profile, and we talk about the deviation that you might have, and then the actual filter design that we are studying. So in the end, this becomes a valuable piece of information that we give during our factory acceptance testing, part of our output. So let's move on. So we're talking about some things that we might catch. And if I go to the next slide here, if I have a resistance change, values of resistance within the filter itself, you can kind of see what happens as we change the resistance of the circuit here. You can see that these are just the high-pass resistance value that we're changing. We get a different shape in the impedance curve. So differences in the resistance of the high-pass resistors results in a different shape in the impedance curve. So this is one thing that this device will capture. It will capture that impedance profile and the impact of resistance on the system. And you got to realize when we're doing harmonic filter banks and we're using high-pass resistors, that the resistors themselves are cold. The reality is that there's a cold resistance value and a hot resistance value. And what we do during the test is we'll come up with a test for cold resistance first, and we'll get a more sharp profile. It's not as damped, in other words, it's a sharper profile harmonic filter. And then we will do a hot resistance value. And the way we do a hot resistance value is we have to dub in, basically insert some impedance or resistance into the circuit to create this other profile. So we end up with two test results, a cold resistance test and a hot resistance test. So this is the impact of resistance on the system. And then we have, well, what does changes in inductance mean? And what does maybe changes in capacitance do? These changes or these errors that might occur, and again, it could be a missed nameplate capacitor, it could be a partially failed capacitor, it could be an improperly tapped reactor, it could be an improperly designed reactor, a misplaced reactor within the system itself. There's a whole host of manufacturing errors from our component supplier as well as from us inside our own factory that can result in a shift in the tuning points. So the changes in inductance, changes in capacitance or capacitor reactance results in a shift to the left or to the right, and we are able to identify these errors very easily with this test system. So this is a slide that just talks about it, and we developed this because of our ISO 9001 certification process. We are looking for ways to identify manufacturing errors in harmonic filters. Historically, what we would do, and what most manufacturers do, is they go out and they measure the capacitance, or they look at the capacitance test reports from the supplier of the capacitor bank. They look at the test reports from the reactor supplier. They look at the nameplate. They put it into some type of Excel spreadsheet, perhaps the NEPSI spreadsheet. They put in those values and they get a frequency scan. But this test makes an assumption that everything was manufactured properly at the factory, and the reality is it might not have. And you want to have some other device that's connected external to the equipment that looks into the equipment and checks everything, all the connections. You know, is the neutral been connected, things like that. So we're looking for all types of errors that might have occurred, and this helps to ensure you as a customer or you as an EPC who has come up with a filter design is getting exactly what you asked for. So again, we talked about the test reports. One thing that I want to talk about is this fingerprint here. And this is something that's used by the transformer suppliers. They do an SFRA and a transformer to get a wave shape. But we do the same thing. We keep a digital file of the SFRA scan. If in the future, for instance, there were a fault inside a harmonic filter, the first question somebody will ask is, well, is my harmonic filter, is it safe to use? Is it healthy? Is there damage? Well, the best way to actually determine the health of that harmonic filter system, if you had the SFRA test done when it was new, will be to call NEPSI, say, hey, I need that digital file. I need the actual digital file. You send somebody out in the field and you redo the SFRA test on the equipment and you confirm, has my wave shape changed? Has my scan, my impedance scan changed? If it has changed, you will see it. So we say kind of fingerprint, put a fingerprint on your design. It's going to be an exact characteristic. If anything has changed, you're going to be able to identify that change with the SFRA test set. So what we're going to do is I'm going to run out to the factory floor, and I'll ask you a question. We'll skip out to the factory floor. We have Peter and Jessica out there waiting for us. They're actually hooking up some test equipment. They're going to show you how this test runs, and I'm going to run out there and meet them to do this test with you. Pete, are you ready? Yes, I'm ready. I'm ready to do an SFRA, a sweep frequency resonance analysis. Sweep, huh? Sweep, yes. So for those who do not know, Peter Stetrick is a twin brother. We are co-founders of NEPSI. I have two other brothers in the business. Pete is one of them, and we have Frank Stetrick. Sitting next to me on my right is Jessica Stetrick. So these two are going to go through this sweep frequency response analysis, and they're going to talk about the test, how they do the test, and things like that. And I'm going to leave it to them to do. All right. So we're just about done connecting up the capacitors. We have just two more capacitors to connect to what we call a collector bus here. There's the capacitors are connected to the connector bus through a fuse. And so rather than install all the fuses, we're installing jumper test leads between the collector bus and the capacitors. And I'll just get these connected up. And so what we're looking at here is this entire bank from one end to the other. It's a 25.2 megabar, 4.7 tuned filter rated at 34.5 kV and 50 hertz. It's built to an IEC standard. This equipment is being shipped to Europe, so it has to have that rating. Stage one is a 3.6 megabar bank with 6 capacitors. The second stage is a 7.2 megabar with 12 capacitors, and then third stage is 14.4 megabars with 24 caps. You're looking at stage 3 right now. All the capacitors have been connected. The capacitors, in this one, there's a total of 24, 8 total per phase. There's a split Y, so it's 4 on one side of the Y, 4 on the other side of the Y. The neutral here is connected on this end, and then the neutral on the other side of the Y is connected on this end. The capacitors all feed in, they get fed from some harmonic filter reactors. The harmonic filter reactors are supplied by a breaker. We have already closed the breakers, so we're indicating that the breaker is closed. And so now we just move down to stage 2. Stage 2 is half the size of stage 3, so there's only 4 caps rather than 8 caps. Again, we have a Y connected and a Y connected with a split Y in between. All the fuses have been connected with a test lead. The stage 2 reactors are a bit smaller because the filter's a bit smaller. And again, this is connected with a breaker, and the breaker is closed. So Pete, maybe I ask a question. So you do the test with everything closed? Is that the way you typically do it, or do you do it with the stage open? We can do it either way, but we typically close all the stages because if we run into an issue, saying that we run into an issue where we see an anomaly between the phases, between each stage, we'll then maybe open the stage to try to isolate where the problem is. But we normally do a test. If everything looks proper in the scan, we won't have to open each stage individually. So moving on, just the stage 1, it only has 2 caps. That's half the size of stage 2. And again, split Y right down the middle. There's no connection between, but only through the Y point. And these reactors are quite a bit smaller than the other capacitors. And again, this breaker is closed. So for this, Jess is mainly involved in the testing that requires a lot of technical background. So she's actually in charge of impulse testing, partial discharge testing, and the SFRA. So Jess, why don't you... this connection that you make inside, please, Jess. Yes.
Yeah. So for the SFRA, we use the MegaFrax 150. There's a generator lead, and then there's the measurement lead, and we connect those from phase to phase. So we'll do A to B, B to C, and then A to C. And those are right in there. They're on the incoming bus, so where the customer would connect their source. And
we'll come on over here, Matt. Maybe we can just show what's going on with
so when you come over here, this is the MegaFrax 150, the frequency response analyzer. So I'm going to start by naming my test, which is from phase A to B. And I just hit OK. And right now, if you would like to, you could put in company information and make a more formal report. But since this is just Tech Talk Tuesday, we'll surpass that. And then it automatically saves into a file. So we'll name it Tech Talk. And then for AB, I have my measurement settings. They're set as default right now, so they're all in there. So I'm starting at 20 hertz, so I'm going to sweep this entire unit from 20 hertz, and I go down to almost the 50th harmonic, and we set multiple bands for to speed up the process of the scan. And after that, you can just hit test because we're connected to phase A and phase B, and you hit the test button.
So what it's doing now is it's injecting volts and current into the system and it's measuring impedance, right, as it goes on. Is that true, Jess?
Correct.
Yes.
Yeah?
Yep.
With a phase angle.
With phase angle.
Yeah, which I can show you the impedance phase. No.
So if we had a misconnected capacitor, say the neutral is left out, or the capacitor is nameplated wrong, or say the taps on the reactors were incorrectly connected, we would easily start to see it on this impedance scan because we could compare it against the theoretical and it would show itself.
Yes. Yep. And that's important when you switch from phase A to B and then A to C. We've had tapped reactors, and phase C would be tapped wrong, and phase C would be tapped wrong, and then the tuning point wouldn't match what it's supposed to be, the theoretical.
So what do we have here?
So right here, the test is complete, and this goes down to around 235 hertz, which is 4.7 tuning point, because all the reactors, all stages in this bank are tuned to the 4.7th harmonic. And here it's in frequency, it's in hertz, it's not in the harmonic number. So because it's a 50 hertz system, if you just multiply your 4.7 times your 50, you'll get the tuning point where it should be, which is the low point of the impedance.
So it's interesting, at the tuning point you would expect something very low because X of C equals X of L at the tuning point, and it's just resistance at that point. And this instrument can show resistance also, correct? Or?
Yeah.
All right.
Okay, so I'm going to disconnect A, and we're going to test B to C now, and Jessica will run this test, repeat this test, and then we'll overlay on the top of the first test. And that's the way we do this procedure. We will overlay the three tests onto one another.
All right, so you do A to B, B to C, C to A. You have three tests.
Yep.
And you're testing actually phase to phase rather than phase to neutral. So you have double the impedance.
Correct.
Right, so when you do your report, we end up having to cut it in half. Is that what we do?
Yep.
Okay.
So if I just go in here and I will rename this because we're on A to C, or we're on BC or AC?
BC.
So rename that BC, and then we'll run that test, and this should look exactly like phase AB.
So if you zoom in, you can actually see the scan. You don't want to zoom in, but you can see the scan. One overlays on the top of the other. So if there was say the wrong number of capacitors in this setup that we've assembled, it would show itself right now on the C phase.
Show as a shift in frequency, right?
Yes,
the actual tuning point.
The tuning point would shift at the bottom, right at that minimum point. You would see a difference. And I'd like to perform a fourth test just so we can show that simulation.
So we go.
So now phase A to phase C is the last test to confirm the tuning point of all three phases.
All right, we're on A to C.
So it's really a fast test. It looks like we can get this done in just 10 minutes or so. We've effectively tested the entire harmonic filter, impedance profile, and we can confirm it. Once this is done, you push it into Excel or something, and you plot it against a theoretical.
Yep.
So a very fast process. We used to do this before you came along. We used to do this with Excel spreadsheet, measuring each component, but it doesn't catch the same amount of errors as this does.
All right, so these things are so close that one is almost right on, one line is almost right on top of the other one, as you can see. So would you like to do a fourth test on the same phase? I will remove half the capacitors in the last stage so that we can say, well, maybe there was a reactor that got put in stage 3 that should have been in stage 2, and so now you would see a discrepancy.
All right, let's do it.
So
we're gonna
A and C.
We're gonna simulate a manufacturing error to remove. I realize you're carrying the mic, so what Pete's doing is
I'm on AC.
Well, he's removing some fuses to indicate that, well, maybe we didn't connect a neutral in or something like that. So you're going to see what it looks like when we have a shift.
All right.
Do you want to take
Wrong
that fuse
assembly.
out? Take the fuse out too?
Yeah.
Just so all of them on that side are out.
Yes.
So you're doing another overlay?
Yep, so I'm going to do phase A to C, which is the one that we just did. And I can actually turn all the other phases off, so we're just looking at A and C. And I can run this test, and the tuning point should be shifted from AC, which is there now, without the capacitors disconnected, and now they are out of the circuit, so the tuning point should shift.
Okay, well that is what you call an anti-resonant point. Paul can go into an explanation of that anti-resonant point, but that is a characteristic of like a 5th, 7th filter arrangement. So Paul can go through that anti-resonant explanation.
So the tuning point, he removed some capacitors, the reactor's the same, he moved the tuning point up. So now we have basically a 5th tuned filter and another tuned filter. You have a resonance in between, and we're actually seeing that here, that resonance. I think that explains it.
Yes.
So,
okay.
So sweep frequency response analysis. It's how we do it. It's how we check it at the factory. Jessica has been doing all of them for the past year or so. She's managed to pick up a lot of manufacturing errors at our factory, missing neutrals, tap reactors that are incorrect. Which other ones?
We had a
versus
delta
Y?
connection that was supposed to be Y connection.
Delta versus Y. Misnamed plated capacitor, was that one?
Yeah, when we first got the Frax 150, I did find we had a capacitor, and it was, the part number was off by one number.
And we had one,
found it.
and we had one recently too that's worth noting is we had a resistor connected up wrong, and that resulted in the dampening of the filter being wrong, and we picked up on that one also. So, all right, so I think that just about does it. I'm going to run back to my desk, and thanks.
All right.
Pete. This is Pete, the other design engineer, right? He's another co-founder, and Jessica's his daughter. So, Jessica Stechik, power engineer from RPI. We're all power engineers from RPI. And Matt, holding the cameras, an RPI guy.
All right.
All right.
Thank you.
Thanks, Paul.
All right. Well, that was cool. That was cool. I know it was. Where else can you get such useful information on our factory floor, for sure? So where can you get some additional reading? We have already talked about this on LinkedIn 2 times. We have 2 different articles. So I would reference you to go back to those articles that talks a little bit more about this. Of course, you have this recorded video. All NEPSI Tech Talks are recorded. So go to our playlist. There's 21 of them now. And of course, there's another YouTube video that was produced a while back when we first purchased this equipment with Jessica and myself, also talking about the value of this test equipment. So go to those 3 locations to get some information. And don't forget, I often publish on LinkedIn articles about harmonic filters and reactive compensation. I spend a lot of time developing LinkedIn articles. They're written in a very basic form, somewhat entertaining, I hope sometimes. So go there and to learn more about NEPSI products, and the application of reactive compensation systems. So there are some other tests, and we're going to be doing these other tests in the future. Power frequency 1-minute withstand test and lightning impulse test. Another 2 factory tests that we see is very important. We're going to do the impulse test, and I guarantee you're going to love that factory FAT test, because we will have a little bit of lightning and things going on. Also, partial discharge testing. So remember, impulse testing helps to guarantee that the design is correct. You get the right phase clearances and things like that. You don't have a bolt that's maybe passed through too far. Remember, metal closed harmonic filters and capacitor banks are all custom in nature. And just like switchgear, when it's the first time you build it, you type test. You type test. Why? Because you want to make sure the design is good. Well, if the filter bank or capacitor bank is being built for the first time, the only way to know you're getting what you asked for and that it works is that you did the proper tests. Impulse testing by far is important. And we can't tell you how many times we impulse test our equipment and we find issues with the equipment. The bolt is passed through too far, our phase clearance has been broken. So power frequency withstand test and bringing your system up to the power frequency withstand for 1 minute does not guarantee the phase clearance is met. It just doesn't guarantee it. And we did it that way for years. And we finally did buy this lightning impulse test equipment, and we have learned a lot since then. So if you're specifying an impulse level and you really want to know you're getting it, then ask for the impulse test. Partial discharge testing helps to ensure that your equipment will have a long life. You can pass impulse, you can pass withstand, and then you can fail on partial discharge. Partial discharge measures the amount of corona discharge that you have in your design. Did you go through a barrier incorrectly? If you did, it will show up on the partial discharge test. It would pass impulse because it's a momentary thing, but partial discharge talks about the life of the equipment. It really, when you have corona, you have a degradation in the insulation system. That degradation in the insulation system might take 1, 2, 3, or 4 years to cause a failure, but at some point it will cause a failure. So if you're looking for equipment that's designed for 20-year life, partial discharge testing is something you must specify. And then finally, we did the number 3 item here, SFRA testing. So what I did is I put on this presentation the 3 ways to specify these tests. Okay, the first 2 apply to capacitor banks. All 3 apply to harmonic filters. So specify those. It's a way to guarantee that you're going to get equipment that will make it for its lifetime. So in conclusion today, if you want SFRA testing, specify it, for sure, specify it. And then also specify that you want this Frax 150, the MegaFrax 150. In the process of evaluating these SFRA test sets, we had a couple of them sent to us. The Frax 150 by far, for the purpose of determining the impedance profile of harmonic filters, it was by far the best one. Okay, so we would say the Frax 150. And remember, you want to ask for a test report, you want to ask for the digital file. And if for some reason in the future you have some type of issue with that filter system, you want to make sure that you use the same SFRA test set. It's got to be the same one, Frax 150. And that way you can overlay the plots and you can determine if the system was damaged or not. As a reminder, PDH contact hours, send us an email. The code is 208. 208, send it to us. Either Matt or I will respond with a certificate to indicate how much time you got. And let me see what else we have. And don't forget to ask questions. Come to NEPSI. You can contact Rodrigo Dunner. You can contact myself. You can send us an email or sales@nepsi.com. There's lots of ways to get a hold of us. But come to us for budgetary pricing, footprint, application support, even some basic harmonic analysis at the front of a project, and we can help you determine what you need, what type of filter or capacitor bank you might need. Go to our website. We have product literature, guide form specifications, a boatload of how-to videos, case studies, spreadsheet tools, calculator tools, and we've done some tech talks about these things. So a really good resource for any engineer involved with reactive compensation at the medium voltage level. So we're going to wait for questions. Ask some questions. I don't get it. Nobody's got questions. So I'm going to ask you a question and see if somebody can answer it. What are the 3 tests you should specify to make sure you get what you asked for, to make sure your equipment's going to last 20 years? What are those 3 tests that we recommend? Technically 4 tests. 4 tests. Can anybody put it in the chat box? Nothing coming up on the chat box. Okay, so next week we will be, I think we're going to do outrush reactors, another interesting tech talk where we will talk about the need for outrush reactors. And this is something in particular that is a concern for renewable power plants more than others, and it involves whether or not a capacitor bank needs to be equipped with outrush reactors. So we have other tech talks that we talked about transient inrush reactors for back-to-back switching. Next week's tech talk is about outrush reactors, and we're going to talk about the need for them and then how we calculate the outrush current. So that will be next week tech talk, and we actually will bring you back out to the factory floor again to show you some outrush reactors. See you then.